Alright, this afternoon we're gonna learn another behavior of light which is called a refraction. But before we talk about refraction of light, we need to review the reflection of light. So let's talk about reflection now. In reflection is quite straightforward, and here I have a mirror. And a ray of light will bounce off from the mirror. So talking about reflection, we have a rule which is called the incident angle shall be equal to the refraction angle. So reflection angle. So this is easy. Now, after learning reflection, in this lesson we will learn something called refraction. Refraction of light. So first thing first, I want you to make sure that you know how to spell refraction and make sure you know how to pronounce refraction. And make sure you know that reflection is reflection, refraction is refraction. Make sure you know the difference. Now, what is refraction of light? We actually can observe this behavior of light every day. Now, let's use a small demonstration. Now, here I have a bowl of water and this is a piece of chopstick. So what I'm going to do now is to put this chopstick inside the bowl of water, and it's quite easy for everybody to notice that the chopstick, which is straight, but if you put it inside the water, it's bent. It appears bent slightly upwards, as you can see from this little demonstration. Now, this is the example of refraction. So here we'll come to the textbook. What is refraction? We know that the light travels in a straight line, but that's under one condition, that this light is traveling in the same media. For example, light will travel in a straight line in air. Light will also travel in a straight line in water. But light will not travel in a straight line if it goes from one media into another, just like this demonstration. When the light travels from air into the water, the direction of travel of light will be changed. So this is refraction, or put it into a complete sentence. Refraction means that the direction of travel of the light ray will be changed when it travels from one media into another media. So it appears to us that it's bent. So when we talk about refraction, it's very important that we know several terms. First of all, it's the speed of light in air. Most of us shall know this value by now, 3 times 10 to the power of 8 meters per second. We already refer it as the speed of light. However, to be precise, this value is the speed of light traveling in air or in vacuum. Now, the speed of light traveling in other media will be different. For example, the speed of light traveling in water is not 3 times 10 to the power of 8 meters per second. Instead, it's 2.3 times 10 to the power of 8 meters per second. They are different. So this is something you need to know. So because the light travels at different speed in different media, here we will have one very important physical quantity which is called refractive index. We represent this value using small letter n, which is called refractive index. The refractive index is defined using a ratio between 3 times 10 to the power of 8 meters per second over the speed of light in a certain medium. For example, what is the refractive index of water? Now, the refractive index of water is calculated using this equation. Now, we use 3 times 10 to the power of 8 meters per second as a constant because light always travels at 3 times 10 to the power of 8 meters per second in vacuum or in air. Now, the refractive index of water is given by 3 times 10 to the power of 8 meters per second divided by the speed of light traveling in water, which is 2.3 times 10 to the power of 8 meters per second. Now, if we use a calculator, it's very easy to find that the refractive index of water is 3 times 10 to the power of 8 divided by 2.3 times 10 to the power of 8, which will give us a value around 1.3. Now, because this is a speed divided by a speed, so the refractive index is just a number without unit because it's a ratio. So we can say that the refractive index of water is 1.3. Here's a question for your homework. Now, if I say that the refractive index of diamond is 2.5, so I want you to go back and find out the speed of light traveling in diamond. Given that the refractive index of diamond is 2.5, it should be very straightforward. Now, if we understand the refractive index and we know that light travels at different speed, that is the reason for light to change its direction of travel in between media. For example, I have air on top and water below. So this horizontal straight line will be the separation line between these two media. So we call this separation line as boundary. Boundary, just like the boundary between two nations. It's a separation line between two media. And I have a ray of light coming from the air, and this light is called incident ray. Okay? Do make sure you know how to describe these things because you're going to need them in your questions. So incident ray. This incident ray will incident the boundary at this point. So right at this point, this intercept, we will draw a dashed line perpendicular to this boundary here. And this dashed line will be called normal ray. Well, normal ray is called normal because this is 90 degrees. Just like when we say normal angle, 90-degree angle is normal angle. So this is normal ray. And the normal ray and the incident ray will produce an angle. This angle will be noted as I, which is called angle of incidence. Angle of incidence. After this light traveling through the air and into the water, the direction of travel of the light will be changed. So this changed direction, this ray, will be called refracted ray. Similar reason, the angle between the refractive ray and the normal ray will be called angle of refraction, labeled by the letter R. Now, the incident ray will become a refracted ray when the light travels across the boundary. So we don't like to use this everyday English, so this is called transmit. So in proper physical professional language, we can describe this process as the incident ray is refracted at the boundary of two media and transmitted into water. So we have two different angles. So here we will have a relationship which is called Snell's law. Okay, Snell's law. Snell's law will tell us the relationship between these two angles. And it says that the refractive index of air multiplied by the sine of angle of incidence shall be equal to the refractive index of water multiplied by sine value of R. So if you look at this relationship, it's quite easy to remember. Now, we have the boundary, right? So above the boundary, we will have an angle and a refractive index. Below the boundary, we have another angle and another refractive index. So you don't need to really care about the direction of light going down or going up. You just find the boundary and the sine value of the angle above the boundary multiplied by the refractive index of the media above the boundary. They shall be equal to the sine value of the angle below the boundary multiplied by the refractive index of the media below the boundary. So this is one observation. Another observation is that if we look at this equation, we know that the higher refractive index of the water, the smaller the angle R will become. So by just looking at this direction of bending, we know the water shall have higher refractive index. Now here's the thing. If you compare this diagram with our demonstration over here, previously I mentioned that the chopstick is bent upwards a little bit. But the ray tells us that the ray of light is bent downwards a little bit because the refractive index of air, of water, is greater than that of air. Why is that? So this is about how our brain works. For example, I have a cup of water here, and I use red color to indicate the chopstick, the real chopstick. Okay? Here I have a point P at the chopstick, so light coming from point P will travel along the water, and once it comes to the surface of water and transmits into air, it will be bent because of refraction. Because the refractive index of air is smaller, so the angle here will be greater. So the light will travel in this direction. And here is our eye, and we see point P following this path. Now, this is how our brain works. Our brain always understands an image by assuming that light travels in a straight line. So interpreted by our brain, the point P is actually here. Because our brain will just assume light travels in a straight line. So appears to us that the chopstick below the surface of the water will be moving upwards a little bit. So this is the reason why it looks to us that the chopstick is bent upwards a little bit. So this is the whole idea of refraction. Besides of this, we also need to know how to correctly describe the process by using the appropriate terms like incident ray, refracted ray, normal ray, transmit, right? And refractive index, etc., etc. So you need to go back and make sure you know how to spell and you know how to explain those things in professional physical words. And of course, you need to know Snell's law, which is nothing hard to understand. But before we finish this chapter and move to the next one, I have a little magic to show you. Now, here I have a plastic cup, and I have a 50-cent coin. Now, I put this coin on the table and put the cup on top of it. Now, looking from any angle, the coin is there. All right? Now, here's the magic. I will pour some of the water into the cup. And surprisingly, if you look at this cup now from that correct angle, the coin disappears. But the coin is actually really there, right? Because nothing changed. Because if you really look from top, the coin is there. But you look from other side of angle of sight, the coin is not there. So it's actually using the same physical concept and principle like the chopstick. It's the same thing. It's a trick to fool our eyes, because our brain won't understand the physics. It's our ration. So now, how do we understand this magic? Now, similarly, just like, for example, this is the bottom of the cup. Because of the reflection, the cup will appear shorter. The water inside the cup will appear shallower. Just like if you go nearby the swimming pool and look aside, the swimming pool will become shallower, and until you really jump into the swimming pool, you know that the water is actually not that shallow. So this is also one example of refraction. The homework of today is that you will go back and try to explain this magic using professional physics words. Now, I want you to avoid using these complex equations. So try to explain this magic using a diagram and professional physical words. So this is what you need to do. And also, of course, once you learn this magic, you can go back home and show it to your parents and try to explain the physics behind this magic using your own words. If you can convince your parents, that means you are doing great. Of course, there are lots of magic-alike demonstrations in the science of light. So, for example, if you feel comfortable with all these things, I'm going to show you another one. This is the lens from my camera, right? And this is the laptop screen, of course. And now, if you observe the screen through this lens while I rotate the lens, what you will see? You see that the screen through the lens is sometimes bright and sometimes very dark. I believe some of our students will find this type of lenses in your home. Actually, every photographer has quite a few of these polarizing filters. Now, you will, of course, learn this polarization phenomena in A level, but again, nothing will stop you from knowing more. So if you're interested, after finishing this basic stuff, try to examine and check what is happening over here. But this is only when you have time or use it as a weekend research plan. So that will conclude our lesson in this afternoon. And of course, we will demonstrate in total internal reflections and other interesting behavior of light in the following lessons. So this is the lesson. Any questions?